Good afternoon, everyone. Today is the concluding discussion hour of the Advanced Robotics course 2024, and today I will discuss not much about any specific theoretical concept, but about how to put all these concepts which we have seen to some extent in the entire duration of this course, how to put them together on a real system and make it work in simulation and on also on real hardware. So just to give you a bigger picture of how different components come together and synergize together to make an actual robot walk, right? So as we discussed in the last discussion hour, we discussed about legged robots, and I will continue with a legged robot only, specifically quadruped robot. So let's get started. So quadruped robots, as the name suggests, are robots with four legs, right? So the first thing that we will have to do if we want to make this robot do any kind of motion is to basically build a mathematical model of this robot, you know. So we till now what we have seen that if we have a system connected of multiple links which are modeled as rigid bodies and joints are assumed as frictionless, right? So these are two basic assumptions which we have taken in our derivations. So we will model the quadruped robot like that only. So each leg will have three link. I will mark this as, and the fourth leg, right? This will be the foot. Right, so let me draw the axis also. This is the front of the robot, the plus x direction. This is the plus y axis, and this is the z axis. And we can put the center of mass here. This is the base or the torso. This is the hip link, the thigh link, and we can call this as calf or shank link, right? And this is the foot. So this foot and the calf is rigidly joined, so there is no degree of freedom in between foot and the calf, right? The degrees of freedom are, here is the 3 degree of freedom of the leg, right? So 4 legs, each having 3 degrees of freedom which are actuated. So what are our assumptions for building the mathematical model? First is that all the links are rigid. Second is all joints are revolute. This is not an assumption, this is a fact, and they are frictionless. So As we had seen in the last discussion, that 12 degrees of freedom are the actuated ones, and we have 6 degrees of freedom of the base, which is unactuated, right? So we have total 18 degrees of freedom. So basically, this robot, if you isolate a leg, it's a 3R manipulator, right? So uh, a quadruped robot is equivalent to analyzing 4 3R manipulators, but not on a fixed base, on a floating base, right? Because the base is not base can also move here, right? It's a mobile robot. So 4 3R manipulators mounted on a floating base, right? And since we have quite a few rigid bodies here, we can assign certain frames which are generally useful in carrying out analysis. So I've drawn only one leg for clarity, right? So we use a different color. This is the inertial frame I, which is fixed. This is the base frame. So the base frame is at the center of mass, located at the center of mass, and is oriented as the base is oriented, right? So the orientation of the base frame changes as the base moves. Okay, so it's a body fixed frame for the base. And then there is a hip frame, right? So hip frame. Now from the hip frame, if we sit on the hip frame, then analyzing this leg is equivalent to analyzing a 3R manipulator, right? 3R non-planar manipulator. So it's quite convenient to do the forward kinematics and inverse kinematics first in this H frame, and then from there we can convert back to base or the inertial frame. So whatever be the frame in which we express the position of the end effector, we convert it first to the hip frame, and then once we are in hip frame, it's a much easier problem of solving the inverse kinematics or forward kinematics of a 3R non-planar manipulator, right? So these are the relevant frames, and sometimes we'll not use it now, but you can also see the foot frame. So this is inertial or global or world, many different names. This is base, this is the hip, and this is the foot, right? Now in the hip frame, and for a given leg, so we are just looking at one leg, and we are sitting on at the hip frame of that leg. So we have 3 angles, right? We have the 3 joint angles, Q1, Q2, Q3, right? And the end effector position, let's say PF, in the hip frame is just the forward kinematics of this q1, q2, q3, and if this is known, so the reverse operation would be the inverse kinematics. So that will be given the position of the foot in the hip frame, we do the inverse kinematics to get the joint angles, right? So, and what's the relation between the frames? So hip frame and base frame, they are just separated by a translation. So they have same orientation, they have same orientation, but different origin position. So there is just a difference of translation, which I will denote in this figure, that the base frame is here and the hip frame is here. So it's at a fixed distance, like this is the width by 2, this is the length by 2, right? So from the center of mass, it's L by 2, W by 2 of up to the hip point, right? And since the orientation is same for the hip frame and the base frame, the Jacobian is also the same, right? Whether you write in the hip frame or you write in the base frame. So Jacobian, which is a frame independent matrix, is same for the hip and base frame. So this was the inverse kinematics and forward kinematics, and we also need to work with velocities, right? So for velocities, how do we get, we know the relation. So the velocity of the foot in the hip frame is, first we will need to compute the Jacobian here. So Jacobian, which will take input q1, q2, q3 and express this in hip frame, and this will be multiplied to q dot, right? So q1, q2, q3, right? So we know that x dot is equal to jq dot. So that's the same thing in action here, right? So in the hip frame, this is the velocity of the foothold, right? If you wish to write in the inertial frame, right, if you want to find in inertial frame, then you will have to express the Jacobian in the inertial frame, and joint velocities will remain the same. Right. So now we will move on to so we have seen kinematics. Now we'll move on to dynamics and dynamical model of these robots. Okay, so what do you mean by a dynamical model? So a dynamical model is basically a relation. So it's a relation between the state and the input, right? So it's a function something like this, in which x is the robot state q is the control input and f is the what we call as the system dynamics, right? So system dynamics basically defines that at a given state, if we apply a certain control input, then how does the state change, right? And the way we model dynamics depends on what are the things that we include in our state. That's one thing. What's the and also what are the things that we include in the control input, right? So basically choice of the degrees of freedom included in the state and in the control input, they basically define the complexity of the dynamical model. So the dynamical model can be very accurate, which but that solving that dynamical model, using the dynamical model, will be computationally costly. So increased physical accuracy comes at a cost of uh, higher computational effort, right? And sacrificing some physical accuracy, we can get cheaper or economy in the computation, right? So in the legged robotics literature, both humanoid, bipeds, and quadrupeds, there are four dynamical models that have been widely used, right? So first is the RBD, which is the rigid body dynamics. So this is the most accurate one, and I will discuss about each of them shortly. So and the second is the centroidal dynamics. Third is the single rigid body, and fourth is the linear inverted pendulum, right? So rigid body dynamics is the most general form, considering the only assumption here is that all the links are rigid bodies, that is, they don't deform, they are not compliant bodies, right? And joints are frictionless. So very standard and less number of assumptions here. So, and this involves all the degrees of freedom of the robot, so total 18 degrees of freedom, right? And the equation comes out to be in a standard form of any rigid body system, which you have seen earlier also, that the standard equation is of the form that it's the mass matrix times the acceleration and the non-linear effects, the Coriolis, centrifugal and gravity effects, is equal to the external is equal to the torque, joint torque, right? Now in a legged robot's case, its end effectors, that is the 4 feet, they are making and breaking contact with the environment. So there is an external force acting on the body, right? So basically this robot's leg is experiencing a force here, right? And to experience or to generate that force in order to propel itself or balance its own weight, joint torques have to be applied, right? So in the equation, so basically here the equation has been separated into two parts. The upper one is unactuated the unactuated dynamics, and the lower one is the actuated dynamics. Unactuated corresponds to the base, the 6 degrees of freedom of the base, which are not directly actuated, right? And the lower ones are for the 12 degrees of freedom which are actuated, right? The joint torques. So the joint torques appear here, right? These are the joint torques, the actuations. So they appear in the actuated part of the equation. These contact forces, so this also you have seen in manipulators also, that a force on the end effector is in the task space, and to convert it to joint space you multiply it with J transpose. So J transpose F maps the task space forces into the joint space, right? And here H, as I mentioned, includes all the nonlinear effects and gravity terms, right? Q is the generalized coordinates, tau is the generalized forces, F is the force on the end effector. So this basically is the most general dynamical model of a legged robot, and involves all the 18 degrees of freedom. But using these is also quite computationally heavy, like using this in formulations, optimizations, etc. Right. Now the same rigid body model can be written in a slightly different way by changing the way we look at the system, right? And that's how we arrive onto the second dynamical model, that is the centroidal dynamics, right? So in rigid body equation we have this, right? So we have the external force here, we have the joint torques here, tau, joint torques are acting, right? And this is the base and all. Now so this is one view of the system, right? And torques are also appearing here as the actuations. Now if we look at this system like this, that I have a system, I have the robot, and I take this entire thing as a system, right, on which I have forces acting, right? Forces acting. Now for this system, the total external force will be equal to change in the total external force will be equal to change in the linear momentum, right? So change in the linear momentum, and total moments will be change in the angular momentum, right? So that's the basic Newton-Euler relation, right? Change in total forces is the change in the linear momentum, and total moments are change on the angular momentum, right? So in centroidal dynamics, what we do is we express the momentum, right? Which means, when I say momentum, I mean here both linear and angular momentum. We express the momentum of each link in the center of mass frame, right? So as I mentioned here, we rewrite the center of mass. Sorry, we write the momentum of each link in the center of mass frame and the change of it, right? So the term that you see here, so this basically this quantity is the total momentum in the center of mass frame. Right. So in this equation, the thing on the left hand side is the, if you differentiate, if you see here, if you differentiate it with time, it will be a dot q dot plus aq double dot, right? So this is the change in momentum. So you see the equations in itself, they might look different, but in the end it's just the very fundamentals of classical mechanics. So change in momentum is on the left hand side, and on the right hand side, as expected, we will have the total force acting and total moments. So sum of forces and moments, right? So this is the mg is the weight, sigma fi is the sum of all the contact forces, and the second this lower part corresponds to the torques or moment generated at the center of mass due to the contact forces, right? So basically, if this is the center of mass and the force is acting here, right? So this distance, the distance of this foot from the center of mass, so this is what this term gives, right? And multiplied with the force, right? So r cross f is the torque. So centroidal momentum, centroidal dynamics also captures the entire 18 degrees of freedom, right? Also captures the entire 18 degrees of freedom. There is no sacrifice in the accuracy here. The benefit that we get here is that from our dynamics equation, joint torques have been eliminated, right? We have written the dynamics independent of the joint torques, and that gives us a benefit when we use this in our motion planning algorithms, right? Now moving further, now till now the only assumptions we were making about the robot is that the links are rigid and joints are frictionless, and we were using all the 18 degrees of freedom in the dynamical model. But now with few further assumptions, we can simplify, we can get to a simplified, or what we call as a reduced order dynamical model. So reduced order means, whenever you see reduced order models, it means that some degrees of freedom of the system have been ignored or neglected, right? So this is the third one, is the single rigid body dynamics. So name suggests that there is one rigid body, so the entire robot has been approximated as a single rigid body, right? So how to do that, right? So the main assumption is that what we assume is that the limbs of the robot are very light compared to the base, right? And also the second is either they are light and move, and the second assumption could be that if they are not so light but they move very slowly. So the main thing is that the limbs, they do not contribute much to the system's momentum, right? So what we are looking at here, we were writing the change in the momentum of the entire robot, right? We were including momentum of each and every link of the robot, right? But if the legs are light and they don't move that fast, right, the major momentum of the robot is due to the motion of the base, right? So the legs can be neglected, the momentum of the legs can be neglected in comparison to the base. And once we make that assumption, this robot with four limbs can be approximated as a single rigid body. So you can imagine it as a, just as a single body on which there are some external forces, right? This is the center of mass and these are some external forces. So now the equation becomes much simpler. It's just sigma F is equal to ma, and the second part is the sigma m is equal to I alpha plus omega cross I omega, right? So this is the classical Newton-Euler equations for a rigid body, one rigid body, right? Now it's not a multi-body system. We have simplified into one single rigid body, right? And the first equation, r double dot is the acceleration of the center of mass. So mass times acceleration is the total force acting on the system, which is weight plus the sum of all the contact forces. And the second equation is I alpha times omega cross I omega is equal to the total torque due to the contact forces. And we compute the torque with respect to the center of mass of the system. Now this I as a function of theta, which you see here, it is the full body inertia of the robot expressed in the center of mass frame. And usually this matrix is also considered as a constant matrix. So in a default configuration, let's say in a standing configuration, right, which is almost close to what the robot is also while walking, and since we have made an assumption that the legs are light, as the legs will move, the inertia matrix will also not change significantly. So we compute inertia matrix in a default configuration, and we remove this dependence on theta, right? So now this equation and these two, they just tell us about this base motion, right? So involved quantities here are the degree of freedom of the base, the x, y, z, the position of the base, and the roll, pitch, yaw, the orientation of the base, right? So only 6 degrees of freedom. But this model has been very widely used especially in quadruped robot literature, and with great results. It reduces the computation complexity quite a lot, but still keeps all the degrees of freedom of the base and allows us to basically generate a wide variety of motions, right? We can still have rolling, pitching, yaw motions of the base, and we can design those motions while also not worrying about the complexity introduced by the legs, right? So this is one of the most widely used dynamical models in quadruped robots. And finally, the fourth one, which is called as the linear inverted pendulum. So this is the most simple dynamical model of any legged robot, and we have few further assumptions in addition to what we have for SRBD. So we assume that the base is at a constant height, so base height is not changing. There is no angular motion of the base, so we sacrifice 4 degrees of freedom of the base, right? 3 of the orientation and 1 of the Z. So if we do not consider those 4 also to be changing, right, and the footholds are also at the same level, then we can simplify basically the equation into two scalar equations, one in x direction and one in y direction, and here this is the location of the ZMP or the center of pressure. Right. So this is a very simple dynamical model in which the base x motion and y motion is described in terms of basically the position of the COP or ZMP. And again, this model was also used initially quite a lot, and people have shown robots walking in uneven terrain also using this LIPM model itself. So this model also served well, but has a limited capacity of motion generation because we are sacrificing 4 degrees of freedom of the base, so we cannot create motions in which there is a change in orientation, which is required for jumping kind of behavior or fast dynamic gaits in which there is a pitching or rolling motion of the torso. So to conclude, the choice of the dynamical model should depend a bit, considering what are the kind of motions that we are to generate, also what is the kind of computational resources if we want to solve these algorithms using these models on the robot itself, right? So based on those considerations, we can choose the preferred dynamical model of the robot. And yeah, as a famous saying goes by, all models are wrong, some are useful, right? So we should keep that in mind, that even if our models, we use the RBD model, it's not a guarantee that the motion that is generated by that model will be followed very accurately on the hardware. The reality cannot be modeled by a set of equations, right? So now, as I mentioned at the beginning of the discussion hour, that we will see how all these different things are put together and where they come into the bigger picture of making a robot move in the real world, right? So this flow diagram basically shows the overall architecture that is being used on the Swan quadruped robot, Swan M2 quadruped robot, right? So the user can command the robot to move in a certain direction using a joystick, and it can command velocities in the x, y, and yaw direction, right? So it can command either move forward or back, left or right, or turn left or right? These are the 3 sets of commands it can give. Now based on those commands, there is a planner, which we will see shortly, which generates where the legs should step, right? Where the legs should step and where the body should go. So, and that is the function of the planner, right? The planner generates the reference commands of where the foothold should be for a leg and where the body should go, such that the body remains, or such that the robot remains stable. Now these, once we know the commanded base position and also the foothold, we can use inverse kinematics to generate the reference joint angles, right? And these reference commands are sent to the controller, right? Now the task of any controller is to generate the torque commands, right? The torque commands are sent to the robot, which has these actuators. In these actuators, the torque commands are sent using BLDC motors, right? And the legs are actuated, right? Now once the motion happens, and you will remember we had seen this in closed loop control when we were discussing, we get data from sensors, right? Now using that data, we estimate, right? We estimate where different states of the robot, right? We estimate what's the robot state, and in that we estimate the xyz position of the base, the roll pitch of the base, right? We get the joint angles, joint velocities, and also which leg is in contact and which is not, contact state, right? And using all these information, we send it back to the planner to let it know the updated information about the state, and accordingly, if there is something that needs to be adjusted, it is being done in the planner, and updated reference commands are sent, right? So this loop is being executed on the real robot like 200, 300 or 500 times in a second, right? So basically this is what we will see, call it as a closed loop control of the robot. So now we will again look into these blocks one by one. So what the currently, as I mentioned, a widely used model for the robot is the SRBD model, and this is what is being used in the balance controller which I showed above this block. The SRBD model is being used, and as I mentioned above, in the SRBD model, this robot with its 4 legs is approximated as a single rigid body on which forces are acting at the contact points, right? So these legs which are encircled, they are the legs in contact, and forces are acting at those points, right? Now the idea, now first we will see at the what is the what does the balance controller do, right? So the aim of aim of this controller is to decide what forces should be applied on the legs, or what forces the legs should apply, which are in stance of course, in order to create or in order to apply a certain desired force and torque on the base, right? So we should remember that the base cannot be actuated directly. So if we want to apply a certain base and moment on the apply a certain force and moment on the base, that has to be created by applying a required force on the ground by the legs in contact, right? So that's the primary objective of this controller. So, and the dynamical model that we use is the SRBD model. So this is the same equation which we have seen above, right? So this is the uh, force, the contact force, right? So contact force, sum of contact force is equal to the mass times acceleration, and sum of all the torques due to forces at the contact is equal to I times alpha, I alpha, right? So each leg can be either in contact or in swing phase, right? So when it is contact, we have 3 components corresponding to that in x, y, and z direction, and for legs in swing, they do not exert any force, so the forces for them are kept as 0, right? So as I mentioned, the dynamics of the legs are ignored, and for torso also, here you see that only I alpha term is taken. The omega cross I omega term is also quite small in comparison to this I alpha term, so that is also ignored. Okay, so now so the goal of the optimizer is to choose forces such that this dynamics is satisfied, and this B term is achieved. This is the dynamics, right? This is the force, and the vector B here basically has the required forces and moments that is needed on the torso, right? So now we have to see how this B term is created. What is there in this? We have this. So this B is the required force and moment on the torso, and this is also collectively called as a wrench. Now B is equal to this desired acceleration of the center of mass plus gravity and this I alpha, right? Now the way we choose these two terms is also interesting. So we have to track the reference motion of the torso, right? So we will be specifying certain position, velocity, orientation and angular velocity for the torso, and we need to track that. So these acceleration terms, these are found by applying a PD control. So PD control we have seen, right? So this is PD control on the position and orientation of the base, right? So this is the position part, this is the velocity part, this is the orientation part, and this is the angular velocity part, right? And these Kp, Kd are the gain matrices, diagonal gain matrices. So by doing this, what we are trying to do, if we use such a PD control law, the desired accelerations would be such that the actual state of the robot goes towards the reference or the desired state of the robot, right? And so this is the desired wrench on the torso. This is how we calculate the desired wrench on the torso. Now the goal of the controller is to distribute the ground reaction forces and to drive this model to this desired wrench, right? This is the desired wrench, BD. So as I mentioned, we need to compute these F such that this B is achieved, right? Now these forces are computed. By solving an optimization problem, right? So why optimization problem? Because if we, finally we need to solve this, right? AF is equal to BD. So we could have also just done F is equal to A pseudo inverse BD, right? So this was one option, but in order for improve numerical stability and also to satisfy some additional objectives, we formulate it as a least square problem, a quadratic program. So the first term here that you see, that is basically doing the same. It is trying to drive AF as close as possible to BD, right? And this S matrix is a diagonal matrix. It's a diagonal matrix which has weights, and these weights decide so these weights across the 6 dimensions, 6 degrees of freedom of the base, they decide which degrees of freedom dynamics we want to satisfy as closely as possible, right? So if we give a higher weight to, let's say, Z height, then the dynamics of Z will be the solver will try to satisfy that dynamics in a more as closely as possible, right? Now there are two more terms added here. First is alpha times norm of F, and second is beta times this difference between F and the previous optimal value of F. So this alpha times norm of F, this is for force minimization, right? So since we are minimizing this objective, if we minimize this term, then the magnitude of the force will be reduced. So So why we do this? Because if we want to achieve as good as performance, but not keep the forces very high, because higher forces will lead to higher torques will again draw more current from the motor, and the energy efficiency will not be very good. And the second term, this beta times f minus f previous, so taking norm of this difference, what does this ensure is that the optimal value at this time step does not change a lot from the optimal value at the previous time step. So this is what we call as smoothing, right? So this is ensuring that the value of the optimal force does not change a lot going from one time step to another time step, because again that would lead to torques that have very fast changes in between them, and the actuator might not be able to follow it very accurately, right? So these are the three cost terms in the optimization problem, the QP problem. And there is a constraint also, right? Because we are solving for forces, and contact forces have constraints. So constraint is the friction constraint. So this CF is less than D is the friction constraint, and this constraint is that the force in x direction should be less than equal to mu Fz, and similarly force in y direction should be less than equal to mu Fz, right? So this is the Coulomb friction constraint. And this approximation, so usually it's a friction cone, right? But this one is a friction pyramid. So again, friction cone would lead to non-linear constraints. In order to linearize the constraints, because a quadratic program should have a quadratic cost function and linear constraints. So in order to linearize the friction constraints, the cone constraints, the Coulomb cone constraints are approximated as a pyramid, right? So using the absolute value function. So these constraints ensure that the friction constraint is satisfied, and also a constraint is applied that the normal force is positive. Now this optimization problem is solved at each time step, and it gives us the required ground reaction force. Now this is for the stance legs, right? So for stance legs we solve the QP problem and get the forces. Now what about the swing legs? Now for swing legs, so swing legs can be treated separately because their motion is happening and they do not affect the other things much, right? So for swing leg we use inverse dynamics control. So we have a feed forward torque, right? We have the feed forward torque term, and we have the feedback term. So this first term here, first two terms are the feedback terms, and this is the feed forward term, right? So feedback term is basically again a PD control law on the position and velocity of the swing leg in the task space, right? So this is the task space formulation, because this is the position in the task space and this is the velocity in the task space, right? So PD in the task space and adding a feed forward component to it, right? So that gives us the torques for the swing legs. And to convert for the stance legs, to convert the torques in the forces into torques, we use again this relationship. So this is basically tau is equal to J transpose F. This rotation matrix is used to just to convert the or to change the frame of the uh, feed force, right? So we get the torques, and once we have the total, so once we have 12 cross 1 torques, those are sent to the actuators, right? So as I mentioned here, these torques are sent to the actuators. So this is the summary of the balance controller. Now what's there in the planner, right? So as I mentioned, the planner, what it does is it selects the or decides where to step next, right, based on the commanded velocity of the robot. So here what we use is that the next stepping location is the current location of the hip. So location of the hip is basically this thing. This is the location of the hip, right? And we add a certain term which you can see as the stride length, the reference stride length, which is the desired velocity of the base and the stance duration, right? So velocity times the time, velocity into time is the distance that the leg should move ahead. And there is a another correction term which basically accounts for if there is a disturbance or tracking error in the velocity, then it should step accordingly, the robot should step accordingly in order to correct itself, right? So let's say if the robot is going in plus x direction, and if I push it slightly, give it a push, then there will be a difference in the actual velocity and the reference velocity, right? And the robot should compensate for it in order to keep itself stable and not fall down, right? So that's the behavior which is emerging from adding this term in the foothold planning algorithm, right? So the footholds are planned like this, and once we get the foothold, from the takeoff point to the foothold point we fit a swing trajectory. So we know the takeoff point, we know the landing point, so we fit a trajectory, right? That this is how the foot should move from this point to this point. We use certain height from the terrain that it should achieve, right? This is the z height, and different there are different choices of trajectories that we can take. A very common one is the cubic Bezier curve, right? So once we know this trajectory, we can sample points on these trajectories and accordingly do inverse kinematics to get the joint angle trajectory for that swing leg, right? So this is how the planner works. Now I will just quickly show a clip of a simulation which is basically putting everything that is there in this block, the planner, the control and the estimation, and making the robot move around. So this is the trot gait in which two diagonally opposite legs are moving together, and this is being commanded using a joystick, right? So first it is being commanded to move ahead, right? Then it will go around, right? Moving in XY direction both at the same time, right? Then taking a turn. Right, so basically this will give you an idea that what are the things which, you know, this I have just barely scratched the surface of it, but still just to give you a flavor of what are the things that go in order to make a robot move around, right? And this is, I just showed you an example of the simulation. In order to take this to hardware, there are an additional set of challenges which come, you know, in interfacing the software with the hardware. There are issues such as latency, noise, you know, computational challenges. So we need to take care of all those things too in order to make it work smoothly on hardware also, right? So basically, this is what we have seen in this course, right? And we started from the very basics of robotics by assigning frames to rigid bodies, using DH parameters, understanding what are transformations between those frames, the rotation, translation, transformations, homogeneous matrices, right? Once we were comfortable with transformations, we started with kinematics and discussed about forward kinematics, inverse kinematics, going from task space to joint space and back from joint space to task space. And while working all the time on different kinds of manipulators, right? And then we discussed dynamics, in which we saw about the Newton-Euler equations, the forward iteration, the backward iteration, and finding out the required torques given the joint accelerations, or if the torques are given, then finding out the accelerations. Then we also saw how to get the equation of motion of a system, right? It can be either through the Newton-Euler equations or using the Lagrangian method, which is energy-based method, right? In which we write the Lagrangian of the system and then use the Euler-Lagrange equation to basically get the equation of motion and get the mass matrix, Coriolis matrix, gravity, etc. And then we moved on to the control part, in which we saw, basically first we saw how to, what's the you know idea of controlling a system by using a very basic second order differential equation, and we saw how just by varying few parameters different kind of responses can be achieved when we excite that system. We saw about critical damping, over damping, under damping, and how they relate when we are actually designing, let's say, PD control laws for joint angle tracking or making a manipulator follow a certain path, right? And that basically builds up to this point where more comprehensive and basically complicated controllers have been developed in order to control robots like these. So in last class we introduced legged robots, which, so very different to the fixed base manipulators which we had seen up till then. And these mobile robots which can go around, have a floating base system in which limbs are attached and they are making and breaking contact with the environment. They are a very complicated systems and challenging to balance and make them do agile maneuvers. But the the research in these areas has progressed such that now these robots are quite agile. They can move over highly uneven terrain while keeping themselves stable. They are actually working in outdoor environments, right? But there are many challenges still that need to be basically solved for. So with this I would like to conclude this discussion hour, and yeah, maybe we will meet in next year in some other robotics course. So till then, goodbye and good luck.